So for the last little while, we've spent a significant amount of time on Newton's second law, using F net equals ma in a variety of contexts. At this point, you've seen enough situations where you should be able to handle Newton's law with a great deal of comfort. When we talked about Newton's laws generally at the very start of this unit, we said that there were three laws. So the first law has to deal with what we call the law of inertia. An object will remain at rest or at constant velocity unless acted on by unbalanced forces. So basically in objects, if there's no net force acting on the object is going to continue doing exactly what it's always been doing. Newton's second law, F net equals ma. So the last thing we have to talk about is Newton's third law. Those of you that do some more physics at the post-secondary level, you'll do a lot more calculations with this. In high school, we don't really do a lot of calculations with it. We use it as more of like a theoretical, kind of as a theoretical springboard. And especially when you do physics 30 and do momentum and impulse, you'll talk a lot more about the third law. So here's the deal with the third law. When you have two objects interacting, there's always going to be two forces and they act as a pair. So one of these forces is what we're going to denote as the action force. The other is what we're going to call the reaction force. You may have heard the expression for every action there's an equal and opposite reaction. That's essentially what we're getting to, but we have to be really, really careful with that. When we're applying Newton's third law, it's a small detail, but it's really important. It's that the reaction force, it always acts on a different object than the action force. So the reaction and action forces are not acting on the same object. If they did, nothing would actually happen. So the action and reaction forces, they're going to have the same magnitude. So the numerical value attached to them is going to be the same. The key is that they're going to be in opposite directions. So this is basically the gist of Newton's third law. We can kind of look at it in the nice wordy way. So you could say object A exerts a force on object B, then B is going to exert a force on A that is equal in magnitude and opposite in direction. So that's the nice wordy way of saying it. The mathematical and very nice way we could say is something like this. The force of A on B is equal to the negative of the force of B on A. So when we see this AB subscript, this means A on B. When we see this BA, this is B on A. So this is telling us that the force of A on B and the force of B on A, exact same value. The negative here is just telling us that they're acting in opposite directions. So, for example, if I have a person here, let me sketch this, and they decide to push on the box, well, they can apply a force. So there's a force of, we'll say, the person on the box, so P on B, but at the same time that this person pushes on the box is going to apply an equal force in magnitude, but opposite in direction on the person. So we could kind of say F box on person, or FB on P. And this always applies. If you punch a wall, for example, or a person, not that you would do that, you can supply a force on the wall, the person, whatever, and that's that person or that wall or whatever you've hit, they're going to experience a force. In return, or as a consequence, that object that you've hit is also going to apply a force back onto you. Now, the big thing is, and I mentioned when people like to think of Newton's third law, they talk about this action, for every action there's an equal and opposite reaction. That is a nice way to remember Newton's third law, but it misses that key minor point that I was mentioning, and it doesn't mention that the two forces act on separate objects. And that's the real big key that we want to remember with Newton's third law. The action force and the reaction force, they act on separate objects. Because think of it, if they acted on the same object, they're equal in magnitude and opposite direction, that would just give you a net force of 0. So if I pushed on something, it shouldn't actually move. That's the key. They act on separate objects. So when we're talking about action-reaction forces, we could talk about action-reaction forces acting on objects like in physical contact. Probably one of the best known examples of this would be a firearm recoil. For those of you that have used a firearm, if you shoot it, you're going to notice it kind of kicks back and pushes you back. How much it pushes you back depends on the firearm. Like there's a difference between shooting a 9mm versus a 12 gauge shotgun. So what's happening in a firearm is when you pull the trigger, those gases inside the firearm, they're going to ignite and they're going to push that bullet forward. At the same time that that bullet gets pushed forward, the bullet is going to push back on the firearm. So you, as the person holding the firearm, you're also going to get kicked back a little bit. This is a consequence of Newton's third law. And you'll see lots of applications of Newton's third law in life. Like, for example, the whole ability to walk, that's Newton's third law. When you push on the ground with your foot, the ground is going to push back on you with an equal force in opposite direction. If you want to go swimming, as you push back on the water with your hand, the water is going to push you forward. So Newton's third law, even though we're not going to talk about it in the same amount of depth as we did with the second law, it's actually a significant part of just our daily, everyday being. And try to think about the things that are Newton's third law scenarios as you're kind of working your way through the world. The other type of action-reaction forces we can kind of look at things when the objects are not actually in contact. And for a force to exert its influence, the objects don't need to be in contact. For the example, the force of gravity experienced by an object near the Earth's surface, the object doesn't have to be in contact with the Earth for that force of gravity to be experienced by said object. For example, if you jump up in the air, you are going to get pulled back down to the Earth's surface due to the force of gravity. You are not in physical contact with the Earth when you jump in the air, but you can certainly feel its influences. And when we talk about these action at a distance forces, we're going to explain these using the concept of fields. Fields is something we're going to discuss a little bit later when we talk about gravitational fields in more depth. You'll also talk about them a little bit more in Physics 30 when you look at electric and magnetic fields. The main thing, though, you have to remember, though, with action and reaction pairs, the pairs are going to be the same type of force. What we mean by that is, like, if one object's exerting a force of gravity on the other, that object will also exert a force of gravity back. Take, for example, here we have this apple falling towards the Earth. So we could say that the action is the Earth's force of gravity is pulling this apple down towards the Earth. The Newton's third law pairing for that, well, if the Earth is going to pull the apple towards the Earth, by Newton's third law, the apple is also going to pull the Earth towards it with the same magnitude of force. Now, the apple having a very small mass, we're going to notice the effect on that force very well. The apple's force on the Earth, we're not going to notice that at all, just because the Earth is really, really, really massive. But kind of the same thing. If you're jumping up in the air and the Earth pulls down on you, you are also pulling back on the Earth with the same amount of force. Just we notice the effects of the Earth's pull on you versus your pull on the Earth, just because at the end of the day, Earth is much more massive. But that's the main thing we always want to be mindful of when we're dealing with Newton's third law. When we're talking about the action-reaction pairs, the forces are always going to be of the same type. And this is pretty much all we're going to talk about with Newton's third law. It will be discussed in other contexts throughout Physics 20 and 30, but we're not going to be doing a lot of in-depth calculations with it as we did with Newton's second law.